Welcome to the fourth lecture of second week. We will continue our discussion on micromechanics of composite plies. In the last lecture, we talked about the equivalent shear modulus of composite. Now, today we will talk about the Poisson's ratios. Now, these composite materials are orthotropic in nature. What is meant by orthotropic? We will discuss that later on in the next week. So, these materials are orthotropic. So, here we talk about two Poisson's ratios. One is a major Poisson's ratio and another is minor Poisson's ratio. So, we will talk about the major Poisson's ratio, major. So, here we have in the composite ply we have fibers oriented in direction 1. So, major Poisson's ratio means nu 1 2, that means lateral strain in the direction of 2 divided by the strain in the direction of 1. If I again go to the idealized diagram that we have been using so far, this is how it looks. So, we have fiber at one side and matrix at another side, and then we have direction 1 and direction 2. Now, if we apply a load in direction 1, then under this loading the deformed shape would look something like this. So, it would deform, it will extend in direction 1, and due to the Poisson's effect it is going to contract in direction 2. Now, the ratio of the lateral strain in direction 2 divided by strain in direction 1 is called Poisson's ratio. So, nu 1 2 is minus of epsilon 2 by epsilon n. So, this is Poisson's ratio, the major one, and we have put negative sign here because we want this quantity to be positive. Now, under this kind of loading the direction 1 experiences a positive strain which is tensile, and direction 2 experience negative strain which is compressive. So, if I put a negative sign for compressive strain, then this quantity becomes, I mean epsilon 2 becomes negative. So, keep to keep nu 1 to positive, I am putting a negative sign here. Now, when this kind of loading happens, our assumption is our consideration is fiber and matrix does not slip, and that is why the strain in fiber and matrix are same, but that means that strain in fiber and matrix may not be same. So, in the epsilon in the second direction there is some change in length, and if we call that change in length delta, then that delta has contribution from both fiber and matrix. That means change in length in the fiber part and change in length in the matrix part. So, change in length in the fiber part can be denoted as epsilon 2 in matrix multiplied by T m. That means, this dimension of this dimension T m, that is the width of the matrix part, and T f is the width of the fiber part. So, delta m is epsilon 2 m multiplied by T m. Accordingly, delta f is going to be epsilon 2 f multiplied by T f. So, this is our total contraction in the fiber part and the matrix part. If I add them up, that we get the total contraction. Now, we can say like we did before, that epsilon 1 f, that means longitudinal strain in direction 1 for fiber is equal to that same thing for matrix is equal to epsilon 1. Now, from the definition of the Poisson's ratio, we can say that epsilon 2 m is equal to minus nu 1 2 multiplied by epsilon 1 m. If I go by this definition, and if we say that our we are evaluating it for only for the matrix, then we can write it like this, which is equal to minus nu 1 2, and this the suffix m has to be there because this nu 1 2 is for the matrix. So, nu 1 2 m multiplied by epsilon n. Similarly, epsilon 2 f can be written as minus nu 1 2 f into epsilon 1 f, and this can be written as minus nu 1 2 f multiplied by epsilon 1. So, we can put everything here and we can write minus epsilon n into nu 1 2 f multiplied by T f plus nu 1 2 m multiplied by T m. Now, we are talking about an equivalent Poisson's ratio, which we can denote as nu 1 2, and that is for the composite. So, if that is so, then we can write that the total contraction in second direction based on nu 1 2 is nu 1 2 multiplied by epsilon 1 with a negative sign into the total dimension T m plus T f. Now, we can cancel epsilon 1 from both sides, we can bring this T m plus T f in the denominator in the right hand side, and we again know that T m by T m plus T f is equal to V m, and likewise we have T f divided by T f plus T m, and that is equal to V f. So, with that said, we can write now the equivalent major Poisson's ratio for the composite nu 1 2 as nu 1 2 f multiplied by V f plus nu 1 2 m multiplied by V m. Now, again in this relation we can see that for the composite nu 1 2 is a weighted combination of the individual nus of fiber and matrix, and where the weights are the volume fractions. Now, this matrix is generally homogeneous. So, because of that nu 1 2 is generally can be written as nu m. So, we can get rid of this 1 2 because these matrices are isotropic, and that is why this matrix has major and minor Poisson's ratio same. However, the fibers is not always isotropic, there are some fibers which are anisotropic, and that is why we have to differentiate between nu 1 2 and nu 2 1 for the fiber. So, with that we can rewrite this as nu 1 2 V f plus nu 1 2 f V f plus nu m V m, incorporating the fact that matrix is generally isotropic. Now, there is something called minor Poisson's ratio also, and in orthotropic material the minor Poisson's ratio generally follows this rule nu 1 2 into E 2 is equal to nu 2 1 into E 1, which means if we find out one of the Poisson's ratios we can find out the other one. So, nu 1 2 is minor Poisson ratio. Now, we can see that in case of isotropic material E 1 and E 2 are same, and that tells me that V 1 and nu 1 2 and nu 2 1 are same. So, we have found out the elastic moduli and the Poisson's ratios with the help of the strength of material based approach, and we have also parallelly looked into the semi empirical equations for those. Now, we will briefly look into the other approaches of homogenization. So, netting analysis is even a simpler approach, where it is assumed that the longitudinal modulus in a composite is due to fiber only, and for transverse modulus and shear modulus only matrix is accounted for. So, in the previous approaches for everything we accounted both fiber and matrix, but here it is saying that for longitudinal modulus we would involve only fiber, and for transverse and shear modulus we will involve only matrix. That is a much more simplified approach. So, with this generally the longitudinal modulus is predicted to a good accuracy, because we have seen that if the composite has a good amount of fiber, and then because EF by EM is generally much higher than 1. So, that is why most of the a bigger part of the longitudinal modulus of a composite is contributed by fiber. So, this assumption gives kind of satisfactory result, but it underestimates the transverse and shear moduli. We will see later on that the strength of material based approach itself kind of underestimates the transverse and shear moduli, and when we make even more assumption that there is no contribution to the transverse modulus by fiber, this even underestimates more. Now, this approach is outlined in these two papers. Okay. The variational principle based approach is another approach which was initially developed for elastic modulus of metal alloys, and that is isotropic. However, we can take this theory and we can extend it for anisotropic composites also. So, here we will have a very brief overview of that. So, this was proposed by Paul in this paper, and the book by R.M. Jones also described this in good detail. Now, in this approach we do not get the exact values of those modulus, but generally we get a bound for the modulus. So, for example, if we want to find out the lower bound, so for the lower bound the principle of minimum complementary energy was used. We know that in the stress strain curve, if a typical stress strain curve looks like this, then we know that this area occupied by this curve and the strain axis denotes the strain energy, and the other side of the area, which means this area, this is complementary strain energy. So, this is strain energy and this is complementary strain energy. Now, if the stress strain curve is linear, these two energies are same. If they are non-linear, then these two energies are different. Now, in these two terms, the difference is mainly in the state term. So, in the strain energy, the strain or displacement based terms are taken as the state vector. In case of complementary energy, the force or stress based terms are the states, and there we can jump from one energy to other energy by something called Legendre's transform. But again we are not going to go there, we are just going to have a brief overview using this how this principle was used and how the lower bound was obtained. So, for that what we assume is that there is a traction applied to the RVE. So, traction applied over surface of the RVE, and let us say that this gives rise to stress sigma 0 because of this traction. Now, this sigma 0 can have different components, the normal components and the shear components. In fact, if it is 3D, there we will have 3 normal components and 3 shear components, and this satisfies the equilibrium equations and boundary conditions. Now, so based on this if we find out U0 as the complementary potential energy. So, U0 is complementary strain energy, which is also a potential energy, then the actual complementary strain energy U should be less than U0. So, this is complementary strain energy corresponding to sigma 0, and this is the same thing, but actual U is the actual strain energy. So, actual strain energy has to be complementary strain energy has to be less than equal to the complementary strain energy corresponding to sigma 0. So, with that the bound that we get is 1 by E less than equal to nu m by E m plus V f by E f. So, that gives a lower bound. If we solve this inequality, then the lower bound that we get is given by this. Now, for upper bound, the other part of the energy curve was used, that means the strain energy curve, strain energy area. So, for upper bound, instead of, so it uses the principle of minimum potential energy . Now, for upper bound, instead of traction or force, displacement was specified over the surface. Over the surface of the RV. So, epsilon 0 is the strain. So, it can have many components, 3 shear or 3 normal. So, that is the corresponding strain satisfying displacement boundary conditions. So, we can say that U0 is the corresponding strain energy corresponding to epsilon 0, and then the principle says that the actual strain energy U has to be less than equal to U0. So, with that we get an upper bound, and the upper bound says that U should be less than or equal to V f multiplied by V f multiplied by E f plus V m multiplied by E m. So, with these two principles we get the upper and lower bounds of our desired Young modulus. Now, again as I said, this was originally developed for alloys which are isotropic in macro scale, but this can be principle can be extended for finding out the corresponding quantities in anisotropic composite as well. Now, we will go to one important approach, and that is the elasticity based approach. So, in the strength of material based approach, we have talked about an RVE, and in that RVE we are applying some loads, and then we are finding out the solution, and then based on the solution we are defining some equivalent quantities and finding out those quantities. Here the approach is kind of same, but the RV looks different, and also the solution approach is not the approximate strength of material based solution, but here we do a elasticity based solution, theory of elasticity based solution. Now, again let us say that this is our composite ply, and this ply has fibers oriented in certain direction, and then we can take from this we can take an RVE which looks like this. So, let us so this RV under study consists of two concentric cylindrical domains. The inner cylinder is the fiber and the outer cylinder that we consider is matrix. So, we assume that the fiber is surrounded by matrix, and if I find out the area of this fiber and if I find out the area of the matrix part, and then we can find out the volume fractions as well. Now, the same thing if I look it along direction 1 looks like this. So, this is the plane direction spanned by direction 2 and 3, and this is what we see when we look it along direction 3. Now, here generally the assumption that we make is the response of the cylindrical domain is axisymmetric, and if I make that assumption, then many a times we work on this in the cylindrical coordinate system. So, for cylindrical coordinate system we talk about 3 axis systems. One is R is the radial direction, and then we define something called theta, the circumferential direction, and this axis 1 is the axial direction. Now, if we want to dig more deeper into these theories, this book can be referred, and also these papers by Hashin Knott and Christensen also can be referred. Now, let us talk about how can we find out the longitudinal modulus using this approach. So, this is the cylinder that we have as our RV, and we assume that the cylinder is loaded in the axial direction at the two ends. Now, if I look at the same thing in the 2-3 plane, it will look like that. Now, this let us say that the load applied is P. So, the load is such that the resultant passes through the center, so that it does not cause any eccentricity. So, along this axial loading P, we want to look at the response of it, and again if the axial loading is P, we can say that the equivalent stress is P by pi b square, because we know that the outer radius of the cylinder is b. So, the area is pi b square, and that is equal to E 1 multiplied by epsilon 1. So, E 1 is our desired Young modulus in direction 1 elastic modulus, and epsilon 1 is the strain experienced by both fiber and matrix in direction 1. So, if I can find this out, then we can solve this problem and get E 1. So, to find this epsilon 1, we will employ the theory of elasticity based approach. Now, we know that when we apply theory of elasticity based approach, the steps that we follow are generally we write the equation of motion, equation of equilibrium, and then to satisfy the equation of equilibrium we make some assumption, and then we satisfy other conditions like boundary conditions, compatibility conditions, and that gives us some solution, and from that solution we can find out epsilon 1, and then we can find out E 1. So, if we have the axisymmetric response, if the response is axisymmetric, then the equation of motion is equation of equilibrium is del sigma r by del r plus this. Here sigma r is the normal stress along radial direction, sigma theta is same thing along the circumferential direction. Now, because we are working on the cylindrical coordinates, so instead of sigma 1, sigma 2, sigma 3 or sigma x, sigma y, sigma z, we are going to have terms like sigma r, sigma theta and sigma z. So, sigma r is radial stress and sigma theta is hoop stress, or it is called circumferential stress also. So, this is the equation of motion, sorry, equation of equilibrium. Now, we need the constitutive relations, that means a relation relating the stresses with the strain terms. So, we have strain terms as this, and sigma C is the matrix of the material properties. So, C is such that all the diagonal terms which relates the normal stress with that same normal stress is this. And the off diagonal terms, which are this C12 is equal to C23 is equal to C13, and this matrix is symmetric C matrix. So, these are also same, and the off diagonal terms are nu E divided by 1 minus 2 nu E 1 minus 2 nu multiplied by 1 plus 2 nu. Now, if we use this constitutive relation here, then this equation can be written in terms of strains. Then we apply something called strain displacement relationship. That means, we relate the strains with the displacements, and that relationship is epsilon r is equal to du by dr, and then we have epsilon theta is equal to u by r and then we have epsilon z, which is also epsilon 1, and that is equal to dw by dz. So, when we work on the cylindrical coordinate system, we have this axis also denoted as z axis. So, we work on three axes r, theta and z axis, with r being the radial, 3 the circumferential, and z is the axial. So, z coincides with direction 1. Then with that we can combine all the relations and we can write the equilibrium equation in this form: plus 1 by r multiplied by du by dr minus u by r square, and that is equal to 0. Now, we seek a solution, approximation which satisfies this solution. So, for that the assumption that we make is u as this sum n going from minus infinity to infinity a n r to the power n. So, u is a function of r. Now, because the response is axisymmetric, so u is a function of only r, we do not have u as a function of theta, and u is the displacement along r direction, radial direction. Now, if we put this approximation here, if we put this approximation in this equation, then this equation turns out to be just this: n is equal to minus infinity to infinity, then we have a n, n square minus 1, then r to the power n minus 2 equal to 0. Now, here we can see that except for n is equal to 1 and n is equal to minus 1, this term is non-zero. So, if this term is non-zero and if the sum is always 0 for any choice of r, that is only possible when n is 0. Again, this term is non-zero, but the sum has to be 0, and that has to be always 0 for any choice of r. and that is only possible when a n is equal to individual a n's are 0. So, except for n is equal to plus 1 and n is equal to minus 1, this thing happens. Now, so we can say that the feasible solution for this is just this, a 1 multiplied by r plus a 1 multiplied by r to the power minus 1 or 1 by r. So, other than these two terms, the other terms are not feasible. Now, again within this we have to see that within the matrix we have a region where r is equal to 0, because matrix within the fiber we have a region where r is equal to 0, because fiber is the inner cylinder or inner circle. So, at the center if r is equal to 0, then this term is going to be infinite. That means u becomes u has an infinite value at the center of the fiber. So, to avoid that possibility, we have to avoid this term for the fiber. So, for the fiber domain, we can say that u f is just a f 1 multiplied by r. So, we have 0 less greater than equal to r greater than equal to a. But for matrix this problem does not occur, because matrix does not have any place where r is equal to 0. So, for matrix u suffix m, that means u in matrix can be written as a m 1 into r plus, or we do not need this 1 suffix, because there is just 1 values of these things. So, B m by r. So, we can separately write the stresses in the fiber and in the matrix as this. Here this C is the constitutive relation matrix for the fiber only. For fiber, and similarly for the matrix we can write. So, all that we are doing is using this new strain displacement relationship, we are rewriting the constitutive relation, and then this can be written as this. And this is for matrix. Now, after arriving at this, we have to apply the boundary conditions and the compatibility conditions. So, the conditions that we apply here are the following. So, here we apply the boundary and interface conditions. And these conditions are radial displacement at r equal to a is continuous. That means, radial displacement u corresponding to matrix and corresponding to fiber are same at the junction. So, this mathematically says that u f at r equal to 1 is equal to u m at r equal to 1. Then we can say that radial strain is also continuous. Radial strain at r equal to 1 is continuous. This is not radial strain, this is radial stress sigma, and this says that sigma f with superscript r is equal to sigma m with superscript r, both at r equal to a is continuous. Then the outer surface of the cylinder. So, we have inner surface at fiber and outer surface at the matrix. So, the outer surface of the matrix does not have any traction force applied. So, it is stress free. So, the traction free surface we have at r is equal to b, and this says that sigma r matrix at r is equal to b. So, this is at r is equal to b, it is not something multiplied or something like that, equal to 0. And then we satisfy finally the axial loading that we applied. So, the stress resultant at the face where the load is applied is equal to P. So, this condition says that axial loading along direction 1 is equal to P. Now, that axial loading can be thought of as the resultant of the stress sigma z or sigma a at the surface of the cylinder, and that is equal to P. So, after satisfying all these conditions, what we do is we obtain. So, all these conditions gives epsilon 1 is obtained. By this process we will get the other terms also am, bm and f, and that helps us finding out u, but here our interest is on epsilon 1. So, with the value of the epsilon 1 that we obtain, we get E1 is equal to P by pi b square multiplied by epsilon 1, which we already defined before, and then finally the terms become E1f into Vf plus Em into 1 minus Vf. So, 1 minus Vf is just Vm, plus we have a big term which is 2 into Em multiplied by E1f into Vf, and then we have nu f minus nu m square. So, here nu f is nu 1 f, and then we have 1 minus Vf, and then divided by something h in the denominator, where h is defined as E 1 f, then multiplied by 2 into nu m square multiplied by Vf minus nu m, plus we have Vf into nu m minus Vf minus 1, plus we have Em multiplied by 1 minus 2 Vf nu f square plus nu f minus Vf into nu f plus nu f 2 into nu f square plus Vf. So, here we can see that E1 that we derived now, the first part of the E1 is same as what we get from the strength of material based approach, and then we have a big term, and in that big term, apart from the individual elastic moduli and the volume fractions, we have the Poisson's ratios also. So, with that I would like to conclude this lecture. In the next lecture we derive the other elastic moduli and Poisson's ratios based on the elasticity based approach. Thank you.